Okay, so we're doing it. Let's see how far we get. Do we actually get to the very end or not? I don't know how long it is, but it's been a while without actually reading something a little more complicated, but let's see. So first is a message from the team. We're very excited to finally share more about what Extropic is building. Hardware platform to harness matter's natural fluctuations. That's kind of what I thought when I meant in the last video, right? As a computational resource for generative AI. It's funny. It's curious, I guess they specifically mentioned generative AI. Does this novel paradigm of computing practically mean the world extends hardware scaling, enables the accelerators that are many orders of magnitude faster and more energy efficient than digital processors, and unlocks powerful probabilistic algorithms that are not feasible in digital processors? I mean, first of all, so what are these examples of probabilistic AI algorithms? They enable the estimation of the quality of explanations provided by AI systems and enhance their ability to handle uncertainty. Okay, that's definitely something to dive into. Then we have the demand for computing power in the AI is increasing at an impressive exponential rate. Luckily, for the past several decades, the exponential growth to be accounted by increasing computer efficiency. Unfortunately, Moore's law is starting to slow down. The reason this is rooted in fundamental physics. Transistors are approaching the atomic scale. We know all these. And then thermal noise kind of kicks in. Quantum effects kick in. As a result, the energy requirements of modern AI are beginning to take off. So there's a bunch of proposals out there. This is building nuclear reactor-powered data centers. On the other hand, biology is neither rigid nor digital and hosts computing circuitry that is much more efficient than anything humanity has built to date. Yeah, that's kind of like what I said, right? It's the sort of harnessing the natural power of computation that is in nature, I guess. Intercellular chemical reaction networks drive computation in biological system. Intercellular chemical reaction networks. I guess that's how neurons work, right? For example, so there are chemical reactions and those form networks. Cells are small, and as a result, the number of reactants in this network is countable. Therefore, reactions between reactants are generally discrete and intrinsically random. I'm not so sure about that, no. Okay. The relative effect of this intrinsic randomness scales inversely with the number of reactant molecules, and as such, fluctuations tend to dominate the dynamics of these systems. So let's try to unpack this because it's a little. It's not here for anything. It's not here for nothing. So therefore, reactions between reactants are generally discrete and intrinsically random, and the relative effect of this intrinsic randomness scales inversely with the number of reactant molecules. I guess that means the more molecules, the less random. And as such, fluctuations tend to dominate the dynamics of these systems. Fluctuations. Not so sure what that means exactly, but let's go ahead. From these, we can say with certainty that there is no fundamental reason for the constraints of digital logic to bind the efficiency of computing devices. The engineering challenge is clear. How can we design a complete AI hardware and software system from the ground up that thrives in an intrinsically noisy environment? So, yeah, energy-based models. That's definitely something to explore. Energy-based models offer hints at potential solution, as they are the concept that appears both in thermodynamic physics and in fundamental probabilistic machine learning. In physics, they are known as parameterized thermal states, arising from steady states of systems with tunable parameters. In machine learning, they are known as exponential families. Okay, this is just a lot to unpack here. A lot of new stuff in here. New for me, at least. So, EVMs. What are EVMs? Employee benefit management service. No. Oh. Should I clear my library? I don't want you guys to see what I'm searching. No, we're looking for these. So, what are... Oh, No, sorry, that's a search. That's what I want. A class of probabilistic models used in machine learning to capture complex relationships of data. These models associate a scalar energy value with each configuration of variables. Scalar energy value with each configuration of variables, aiming to assign lower energy, I guess optimizing for low energy to correct or zero configurations at real data points. Unlike other generative models like GANs or VAEs or EBMs that directly learn an energy function without relying on latent variables. They encompass various models. I guess what this means, right, is when they talk about latent variables, what this means is, right, like if you're doing some generative stuff, whether it's with words or visual or whatever it is that you're doing, you can't work at the space of words, right? So you have to translate all this stuff into some sort of numbers and whatnot, and that's kind of then becomes your latent space. It's kind of a compressed version. I think that is what it is. While here they'll directly learn an energy function because you're using energy directly. Field networks, Boltzmann machines. Like the thing is, I'm not even sure I know what a Boltzmann machine is. I'm that noobious. Something like a Boltzmann machine is a stochastic spin glass model with an external field named after Ludwig Boltzmann. It is a statistical physics technique applied to cognitive science and machine learning, classified as a Markov random field. Boltzmann machines have a network of units with binary results where weights are stochastic. The global energy in a Boltzmann machine is defined by the connection strength between units and their states. These machines are used for unsupervised learning, aiming to optimize solutions by adjusting weights and quantities. I mean, it's kind of a network, isn't it? They're part of the energy-based models and can be used for tasks like clustering, dimensionality reduction, and anomaly detection. They are, but this just seems to be. So how are the modern neural networks? Yeah, okay, connectivity. I mean, it seems like these are all sort of like fully connected things. Bidirectional connections between all nodes. Okay, node types, visible and hidden nodes. With hidden nodes unable to connect to each other, while visible nodes can connect to each other. The training algorithm is different. Learning process. Learn patterns without typical ones or zero outputs with stochastic binary units to reach probability distribution equilibrium. Applications with okay, so not so good at classifying, I guess. Or yes, no. It just seems like it's a type of binary. Okay. Energy-based models, sorry, and market fields. Adjusting the energy functions parameters to assign low energy to observe examples. Okay, so you're training EBMs by adjusting energy functions parameters to assign low energy to observed examples and high energy to unobserved examples. Okay. So essentially what you're doing is you're tweaking it so that everything that is low energy is correct, everything that is high energy is not correct, and I guess then you define a threshold and often using gradient-based optimization techniques as well, right? So that's just, okay, despite challenges like the intractability of the partition function and potential instabilities. So, code examples. What the fuck? Of energy-based models. That's what I meant. in PyTorch. So PyTorch and these things have actually support for this stuff. So there is a paper on generalized energy-based models. There's a model combining a base distribution and energy function for generative modeling. The training process alternates between learning the energy and the base, resulting in improved sample quality. I'm still not entirely sure I grasp what the difference is between these and sort of a general Mr. Lacan. What the general difference between these and a neural network is. Because in a neural network you're optimizing a cost function. Why isn't that one-to-one to the energy function here? Density, whatever it is. This is a whole new thing. Energy-based models. Two trained components, a base distribution, generally implicit model, which can learn supportive data with low intrinsic dimension and high-dimensional space and an energy function to refine the probability mass. Okay, we'll have to dig into this a bit more. I really didn't get far here, but it says so. Let's just go back to the paper. I'll have to definitely dig more into these. So EBMs offer hints at a potential solution as their concept appears in physics. Exponential families are known to be the optimal way to parameterize probability distributions requiring the minimal amount of data to uniquely determine their parameters. They are thus excellent in the low data regime, which encompasses scenarios where one needs to model tail events in mission critical applications as depicted in figure 1. So the way they achieve this is by filling the blanks in data with noise. They seek to maximize their entropy while matching the statistics of the target distribution. This process of hallucinating every possibility that is not included in the data set and penalizing such occurrences energetically requires the usage of a lot of randomness. Okay. So what this is saying is exponential families. What are exponential families? What are exponent? Why did I copy paste it? In statistics, representing a parametric family distribution is characterized by specific properties. Assemblies include distributions like Gaussian, binomial, multimodal. Okay. It's defined by a probability density function that'll follow a specific form involving the natural parameter, sufficient statistic, base measure, and log normalizer. Whatever all that is, the key characteristic of special families is that the interaction between these components are through a dot product. Assemblies have connection to graphical models, and they are used in various machine learning applications. Also, something I have no fucking idea about. Okay. But essentially what this is saying here is the way they achieve this is by filling the blanks in data with noise. They well, it's describing what they just said before, right? This thing with the energy. So they just fill up something with noise, and then they try to do the whole thing with the energy, where they penalize the right things and the wrong things, and at some point just define an energy cut. This requirement of sampling has been the main limiter in production uses of EBMs. The fundamental reason for this is that sampling from generic energy landscapes is very difficult on digital hardware, which must expend substantial electrical energy to generate the shape of the entropy required for the diffusion process. From a hardware perspective, digital sampling seems quite contrived. Why put so much effort into building increasingly complex, pristine digital computers when the most common and compute-intensive algorithms turn around and pump them full of noise? So what Extropic is shortcutting is this inefficiency, and it unlocks the full potential of generative AI by implementing EBMs directly as a parameterized stochastic analog circuit. Okay, so I think that confirms what I kind of said yesterday, that essentially it's doing, because so far what we know is the whole thing with the EBMs and whatnot is this thing of like this energy function. So it's basically a very specific network where sort of AI, whatever algorithm, that all it does is, yeah, well, it is actually some sort of diffusion, right? Because it's kind of like what the diffusion models are doing as well, right? So you start with a lot of noise, and then you keep getting sharper and sharper. So okay, so I think that's what they're saying is they implement EBMs directly as parameterized stochastic analog circuits. So they're going to be parameterized, and there's going to be an analog circuit. So it's not going to be digital, right? So it's not going to be like the zeros and ones. I guess you can parameterize them. Okay. Based on sampling from complex landscapes. The operational principles of Extropic is analogous to Brownian motion. In Brownian motion, microscopic but lightweight particles suspended in a fluid experience random forces due to the many collisions with microscopic liquid molecules. These collisions lead to the random diffusion of the particles around the vessel. One could imagine anchoring the Brownian particles to the vessel walls and each other with springs, as depicted in figure 2. In this case, the springs will resist the random forces. The particles will prefer to reside in particular parts of the vessel more than others. If one repeatedly sampled the position of the particles, waiting sufficiently long in between samples, one would find that they follow a predictable steady state probability distribution. If we change the stiffness of the springs, the distribution should change. Yeah, okay. It does feel a bit technical and convoluted if you don't know on all of these, because like just so far, like look at how many terms I just have no idea about. So Brownian motion in a medium such as liquid or gas. Explanation for this motion. Okay. Yeah, in essence, I think all that means is like, that's another sort of example of like things that move in a constrained environment, right? And essentially sort of have, if you look at that movement, then you kind of see, you can derive what the probability distribution is, I guess. Microscopic lightweight particles spin in a fluid, blah, blah, blah. A simple mechanical analog to extropic accelerators. Since there are 3 masses in 2 dimensions, the steady state of this device would be a probability distribution over a 6-dimensional space. So the samples may be drawn by repeatedly observing the system, waiting at least the equilibrium time between EQ and between observations. We'll definitely have to do another iteration on these, definitely. But yeah, I guess the parameters in here would be, as they say, the sort of strength of these springs, right? And so based off of these, then you kind of, you can essentially generate the kind of model that you want, right? So there's a dark connection. How much more there's left from the light paper? Not so much. There's a dark connection between this mechanical picture and the parameterized stochastic analog circuits that we make that make up initial accelerators. The lightweight particles represent electrons, and the liquid molecules represent the atoms of the conducting medium, which can transfer energy. Okay. So it's really electrons on whatever atoms of whatever the medium is they chose. So the springs represent the circuit components that can find the motion of the electrons, such as inductors and transistors. Yeah, that's how they basically parameterize the circuit, I guess. Control voltages can be applied to tune the values, exactly. Yeah, that's okay, so that answers my question, that they are definitely going to be parameterizable, which makes sense. You wouldn't want to kind of like build chips for every single use case or everything you want to do. So, I mean, well, that's just stupid, forget what I said. That's just obvious because you need to learn these. That's the point, the whole point of the thing. You actually need to learn, I guess, with the by changing those voltages and currents, you're learning the distribution that you want to actually have in there. Although every circuit is noisy, not every circuit is useful as an extropic accelerator. Making a noise-dominated yet well-behaved device is challenging from an engineering perspective. Thermal fluctuations are small, must be physically small and low power to be strongly affected by them. To make the accelerator out of microscopic components on a PCB, for example, one would have to introduce synthetic noise. Doing so erodes the fundamental time and energy savings and ends up performing similarly to running the algorithm digitally. So the first processors are nano-fabricated from aluminium and run at low temperatures where they are superconducting. Tested several possible with the neuron designs. Some of these neurons are similar to existing superconducting flux qubits. These neurons exploit, so there's actually some similarity to the quantum stuff. These neurons exploit yeah, I know this is how they do the superconducting qubits, the Josephson effect thing. This nonlinearity is required to the device to access the non-Gaussian probability distributions, which are necessary to model real-world applications with that tails. Additional digital Gaussian sampling routines are ubiquitous and highly optimized. So if an analog device is to provide a control speed up, okay, I'll go back to this. We need to unpack this a little bit. But essentially what they're saying is that that's their first chip. It's going to be very small, very low temperatures. Nonlinearity, okay. So these neurons provide the basic building blocks that are combined from a larger superconducting system to form a larger superconducting system. In such a larger system, many linear and nonlinear neurons are combined together to create a circuit that samples from a rich high-dimensional distribution. The neuron biases and interaction strength are all tunable parameters of the distribution, allowing for a single device to embody a wide family of probability distributions. Passive, we only expend energy when measuring or manipulating its state. This likely makes these neurons the most energy efficient in the universe. This system will be highly energy efficient at scale. Extropic targets low volume, high value customers like governments, banks, and private clouds with this system. Okay. Also at room temperature. Okay, that's interesting. For the transistor, so they actually use transistors. Interesting. GPU-like expansion cards from form factor. Home device. That's very cool, actually. If this is something they can actually really put into normal computers. Software layer that compiles from abstract specifications of EVMs to the relevant hardware control language. This compilation layer is built upon the theoretical framework of factor graphs, local chunks. This also is to break down programs that are too big to fit in any given analog core. Many previous accelerators companies have struggled to find an advantage because of the memory boundaries in learning. Today's algorithms spend on the time moving numbers around in memory. To achieve more than 4x speed up, as Extropic chips natively accelerate a broad class of rapid energy, we are bound to unlock a whole new regime of acceleration. I mean, that is true, right? If they, if they actually achieve that speed up, I guess what can go wrong, right? So is that the end of it? Yeah, that's the end of it. I guess what can go wrong is that basically in practice that speed up is not there for whatever reason, right? Because I think if you assume the theory is there, as in like the actual, the well, and then accuracies as well, what we're looking for here, right? because I know, I guess the thing is with quantum computing stuff, the main challenge you're going to always have is error correction, right? And because you're always going to have like errors when measuring the qubits and stuff like that. And here they don't dive into the measurement aspect of it a lot, but I guess there's also going to be some sort of error correction that needs to be in place, and that error correction is going to be software based probably, which is going to mean that, you know, it adds definitely like an additional slowdown factor. I guess the point here is it could be that because of some of these factors, this still does not bring that speed up, but I have the feeling that they have a lot of moving room, because I think the theoretical speed up is just so huge that even if they end up eating up a large portion of it, it's still faster than any other acceleration technique right now, I guess. And essentially, I think, if I understand this article well, and I don't, obviously, because I don't understand EBMs in detail, I don't understand all the Boltzmann machine stuff, I don't understand probabilistic AI algorithms, but those are maybe two things to explore in follow-up videos: EBMs and probabilistic AI algorithms. Yeah, but it's what I think it's essentially what I said, right? I think I can confirm that this is what it is. So it's basically a chip that what it does is this: it implements some sort of analog system, that an analog system that can represent a probability distribution. And so they do this by playing with electrons and then confining them within the atoms of whatever the medium it is. And then they have, like, by tweaking sort of voltage, then you can tweak sort of you can configure, I guess, the movement of these electrons, and hence however they're reading these afterwards, because I don't think there's anything about readouts in here. Am I searching? Readouts, read, no, nothing. So I guess that's the next thing, is just to understand what are the references, by the way? The end of Moore's law, kinetics. Okay, I guess we'll have to, one thing that we'll have to, do they have anything in GitHub? Okay, no public repositories. I guess we'll have to definitely explore a bit more about what the EVMs are and what the probabilistic AI algorithms are. But essentially, that's what this is, right? Is a way to basically just, instead of doing matrix multiplication, is a way to just fine tune a chip so that it learns a certain noise function, a certain energy function. So it, which then, by putting the input, shooting the input in there, I have no idea how, and then reading whatever thing out of that, I don't know how, that does by itself the computation. It's like, I'm probably going to exaggerate these, but essentially it's like saying, going from, like, even if it's just like linear complexity time, or, you know, or exponential, no, or like linear, like whatever, like going from ON to even O1, right? It's almost like linear, right? Because it's just like you're doing something to an analog thing and then reading out the result. That something you're doing, it kind of has like almost sort of immediate effects. You wait a bit, I guess, for the system to stabilize. Now, but then you kind of read it out, right? But then the matrix multiplication is much more complex. Now, because you have to move all the numbers around, you have to do all the math and whatnot, right? Now, I think, as I said, noise would be, the measurement element would be interesting to dig into a bit more, right? So how they're, like, is noise going to be a problem for them? Was error correction going to be a thing at all? Maybe I'll ask that maybe we'll ask that in next. Extropic. Is error correction for chips? It's funny because out of the, like, it's funny because like I listened to the comments and the stuff that I've heard so far about these, and it just, people don't seem to be asking the right questions. I think that's kind of probably the most obvious one to ask, right? It's like, say, okay, this is the thing that can pose the biggest challenge in terms of their claims of like the efficiency gains, right? Is error correction going to be a thing? As in, like, how is the reading out, and how they're going to solve these, probably with software. But because that's the main blocker, it's one of the main problems in quantum computing, not just how delicate the things are and how low temperature they must be, but it's like the error correction is one of the current blockers, and it's been for many years and decades, I guess. Anyway, I hope that was useful. I will definitely do more deep dives into these. I don't think there's a lot to unpack in these. It's interesting because it gives it a few more concrete references, but let's just dive into energy-based models and probabilistic S-type in the next videos, while in future videos, whenever they come. See you around.